Okay, we're back. Let us talk about addition of hydrogen onto the multiple bonds. This process is known as hydrogenation, and typically it has to be done in the presence of a catalyst such as palladium. And the main reason this is the case is because the hydrogen-hydrogen bond is a relatively strong bond due to the fact that hydrogen is the smallest element, and the smaller the bond is, the stronger that bond tends to be. So you have to give enough energy just to break that up, and palladium serves the role of facilitating the cleavage, the homolytic cleavage of that specific bond. If you're treating an alkene with one equivalent of H2, you form your regular alkane. You add both hydrogens onto it. But you could do the same thing with an alkyne. You could have the alkyne, and as long as you have enough hydrogen to go around, you will fully hydrogenate the alkyne into an alkane. And this is the whole idea behind unsaturated fats and saturated fats. Um, if you have any type of oils that you extracted from any natural source, you can fully saturate them by hydrogenating them using palladium as your catalyst. But the thing is that palladium is a solid metal, right? And it's not going to dissolve in the actual organic solvent or the alkene or alkyne solvent. So this is actually a heterogeneous process. And what that means is that the process takes place at the surface of the palladium solid. And to give you an idea of how this happens, you could think of this particular palladium atom as being one of the atoms exposed on the surface of the palladium solid. And the hydrogen, when it comes in contact with that surface, what it basically sees is the palladium, which has no charge, and it has these two electrons that are kind of ready to attack. And so palladium attacks H2, through either of these two hydrogens. Right here, I'm just going for the top hydrogen. And when that happens, that entire bond, along with the lower hydrogen, get attached as a hydride onto palladium. And what you end up forming is a palladium 2 hydride complex. This is known as oxidative addition in the world of catalysis. After that, you have your alkene binding to your metal, and the main reason it binds through the pi bond as depicted here is because of a proper symmetrical interaction between the d orbitals of that palladium center and the pi bond of the alkene. So what ends up happening after the alkene addition is that the hydride attacks the alkene. So you literally have an H minus migrating over onto the alkene. Therefore, this is called a hydride insertion onto the alkene. That of course means that if you're gonna bring in two new sets of electrons to this carbon, the double bond is gonna break to create a carboanion on the opposite end, and that carbanion will now bind to the metal as shown right here. So now you have an ethyl group that's bound to the palladium center. And then finally what happens is that the electrons of usually the hydrogen will be given back to the palladium. This will attack the hydrogen, and you'll end up, or shown right here, right? So you have attack onto the alkyl, you have the electrons go back to the metal, you reform that palladium 0 center that you started with, but now you have produced an alkane molecule. And this is known as reductive elimination. So this is one of the processes that you see in catalysis all the time: oxidative addition, alkene addition, hydride insertion, reductive elimination. If you guys ever studied chemistry far enough, you'll get to talk about all of these processes. They're kind of interesting and exciting in their own regard. All right, now to get into the specifics though, what we really need to know, there are different versions of palladium that you can utilize to kind of create different stereochemistry and different stereo selectivity on your products. So notice right here that if we start with an alkyne and we add hydrogen, using something known as Lindlar's catalyst, we can produce a cis-alkene. And what Lindlar's catalyst is nothing more than palladium, but it's palladium that has been mixed on purpose with calcium carbonate. So you only have 5% of palladium in a mixture that contains calcium carbonate. And on top of that, you have lead. You have lead that's also mixed in with this. And pretty much what's happening here is that the lead, which is roughly the size of palladium, what lead is basically doing is kind of occupying sites on that surface of the solid palladium and diluting the amount of palladium present on the surface. So that's the reason why we're using 5% of palladium with these two solids. We're diluting the amount of available palladium on the surface. So yes, that is the catalyst, but the lead, whether it's lead acetate or lead oxide, we call this a deactivator because um, it's pretty much diluting how much palladium is present at the surface for hydrogen to interact with. And then you have these other organic molecules that are technically basic. They can bind very well to metals. Quinoline, excuse me, not quinoline, quinoline, shown right here on the left side, as well as this dithiol molecule. They are very good at binding to palladium, and in essence, they make it less likely that hydrogen is going to be able to interact with the surface because now that surface is being occupied by these groups that are kind of big. So you could think of these groups as the poison of palladium, and so in essence, you are kind of like making your palladium less efficient, but not inefficient to the point where it doesn't react anymore. So that's kind of the beauty of it. Make it a little less efficient than regular pure palladium, and instead of fully hydrogenating your alkyne, you get to only hydrogenate it up to the alkene state. And on top of that, you get to make a cis-alkene. So that's fantastic. We call this a syn addition, so you produce zinc hydrides out of this stuff. So the hydrogens are added on the same side of that alkyne, or what used to be the alkyne. But let's say that what you actually are interested in making is the trans-alkene. Well, there is another way of making this happen, and it is by the nifty reaction of the alkyne with an alcohol, but this is done in a very peculiar solvent. This is liquid ammonia. And in case you don't know, ammonia is a gas at room temperature in its pure state. So to make it a liquid, you have to lower the temperature at the very least down to negative 33 degrees Celsius. Ideally, you want to probably go lower than that because you don't want to be right at the boiling point of ammonia to do this. So if you go below negative 33 degrees Celsius, you got yourself liquid ammonia. And the interesting thing about this solvent is that because it's a cold temperature, even though it's protic like water, it's not as easily prone to dissociate like water is, and the lower temperature also makes it a little less prone to react with metals like lithium or sodium, but it creates a perfect medium to exchange electrons. And so what ends up happening is that you have this radical reaction that gives an electron from the metal, either the lithium or the sodium, onto the alkyne. And so you break the triple bond, you make a new double bond that it's formed with a radical. So notice this, you have an electron coming from one of those bonds on a triple bond, and the second electron is delivered to the opposite carbon of that triple bond. In essence, you form right here that trans arrangement around the newly formed alkene. But this bond right here in red is technically a carbanion that is for the moment being partially balanced in terms of charge by the metal, right? Because this is now lithium plus or sodium plus, but this is still a carbanion. So this is very much an ionic bond, very reactive, and it's a very strong base. So the fact that we have an alcohol present means that the alcohol will be deprotonated by this base. It will form a new carbon-hydrogen bond. And if you compare the pK values of the alcohol, which is about 16, to the alkene, which is 44, you see that via the subtraction, we have a negative value for the pK component of the reaction, telling us that this reaction is indeed product favor. All right, and then at that point you can bring a second equivalent of the lithium 0 or sodium 0 metal to provide that extra electron, create a new carbon ion, and of course at this point you react it with a second equivalent of alcohol via an acid-base reaction to form your trans-alkene. So this is a really nifty way of producing those trans-alkenes from the alkyne. So you're going to have to remember that Lindlar's catalyst to make cis-alkenes, your liquid ammonia with alkaline metal in the presence of an alcohol to make your trans-alkenes. All right. In the next video, we're going to begin talking about the addition of dihalogens onto the bond, and there's plenty to be said about that. So see you in the next video.